So we are studying about the switching devices of the power and power electronics. Okay, power electronics and drives. We are studying the switching devices. First we have studied about diode. Next we have studied about SCR, and the third we have studied about MOSFET. Okay, and now we are going to study about the IGBT. IGBT stands for insulated gate bipolar transistor. So what is going to happen from the name itself? Okay, bipolar transistor. So what so far we have seen, MOSFET is also a transistor, but it can give only in the single direction, right? Single pole. That is from input side to the next that side. So that is here this bipolar, two ways, either from collector to here the terminal is called collector, emitter and gate. Okay, so this is the IGBT symbol, and here the terminals are, this is a 3-terminal device. Okay, 3-terminal device, and the 3 terminals are collector, emitter, gate. Okay, so this can be a configuration, collector, emitter configuration, or else the other combination can be emitter, collector configuration. So we can say that bipolar transistor, collector to emitter, or else from emitter to collector. So conductance happens between whom and whom means collector and emitter. Conductance path is collector, emitter, or emitter, collector. Through it only it will conduct. Okay. So what is the terminal for gate purpose means? The purpose of the gate is to control this. Okay. So we are going to give the gate signal in terms of, we will be saying that as firing angle. Okay. So by means of some signal we can able to control this conductance. Okay. So for that purpose the terminal called gate is over there. Okay. So what we have to for IGBT, you come to know that IGBT is having the bipolar transistor. Bipolar transistor means already there is a device, that is already I told you, bipolar BJT, bipolar junction transistor. Okay, so this is a symbol of BJT. Okay, you won't be studying this working principle. That's a normal one. Okay, so this is a symbol for BJT, and this BJT, that here it is also a 3-terminal device, base, emitter, collector. Okay, so this is likewise the collector and the emitter are conductance part, and the base is to control. Okay, so here collector, emitter, base are the 3 terminals for BJT. Okay, so the once more here it is, whose symbol is this? MOSFET. What are the 3 terminals for MOSFET? That is gate, drain and source. Okay, so here it is single unipolar device. I already told you there is no drain to source or source to drain, just one way of conduction, right? So we can say that it is unipolar or unijunction transistor. Okay, unijunctional transistor or unipolar transistor, whereas BJT is the bipolar transistor, either from collector to emitter or from emitter to collector configurations may happen. Okay, so like this, these two combined from names, what is here? Bipolar transistor. Which is bipolar transistor? BJT is the bipolar transistor. Next, who is here? Insulated gate. Okay, so where is there a terminal called gate to control over in there in BJT? No, the gate is where? Gate is in the MOSFET. So we are going to combine these two. We are going to combine the construction of MOSFET as well as the construction of BJT together to form the IGBT. So IGBT is the 3 terminals are gate, collector, emitter. Okay, so we will be saying that emitter and collector, or else collector or emitter, or the conductance part. Okay, next what we have to say, here gate is to control it. Okay, we are going to control using a gate signal. We will be saying it by generating pulse or by generating firing angle. Okay, later on we will be seeing that what is firing angle. Firing angle will be denoted by the word alpha. Okay, so there is a formula to find out the firing angle. We will be seeing that in detail. Okay, so now gate is to control it. Okay, so the next here in IGBT, if you look at it, okay, here what is the input for IGBT? Gate. And here by whom we will be controlling the MOSFET?
Gate.
The voltage. That is the
voltage is the control.
which the voltage between gate and the source. Do you remember this? Gate and the source. We have given the. Do you remember this VGS?
Yes.
Minus plus V suffix GS. So when we are increasing this VGS, what is going to happen?
Current.
I will show you everything. Okay. So the next the
Drain current.
drain current is going to increase. By that means only we are controlling the MOSFET. Okay. So to MOSFET for controlling using the voltage. So it is said to be voltage control device. Here the input is gate. The input voltage we are varying is VGS, gate source voltage. Here is also who the terminal is gate. So in IGBT also whose characteristics is similar. Its input characteristics is similar to MOSFET. That is important. Okay. So in IGBT, just to compare these two. Okay. Just to என்ன பண்ணிருக்கோம் MOSFET ஓட ஒரு drawback என்ன அது யூனிபோலரா இருக்கு. அதை எப்படி ஓவர்கம் பண்றதுன்னு யோசிச்சுட்டு BJT இன்னொரு டிரான்சிஸ்டர் இருக்கு. So BJTங்கிறது bipolar. It can configure from collector to emitter அல்லது emitter to collector. அதெல்லாம் ரெண்டு டைரக்ஷன்லயும் bipolar டைரக்ஷன்ல அதால ஃபங்க்ஷன் ஆக முடியும். whereas MOSFET ஆல முடியாது. அப்ப இந்த ரெண்டையும் கம்பைன் பண்ணா என்ன ஆகும் அப்படினு சொல்லிட்டு கன்ஸ்ட்ரக்ஷன்ல நம்ம என்ன பண்றோம்? we are combining these two. So while we are combining these two நமக்கு அதுக்கு ஒரு நேம் கொடுக்கிறோம். அது என்னது? insulated gate bipolar transistor. அப்போ bipolar transistor தான் BJT தான் bijunctional தான் அதுல gate மட்டும் நான் என்ன பண்ணிருக்கேன்? insulated. I will just add it. Okay, that is how they do. Gate எங்க இருந்து எடுத்தேன்? MOSFET. So அந்த MOSFET நான் யாரை கண்ட்ரோல் பண்றேன்? I am controlling the voltage. That is gate source voltage. So MOSFET is called voltage control device. அதே input characteristics தான் யாருக்கு இருக்குறா? IGBT க்கு இருக்கு. அப்ப IGBT is also called voltage control device. That is the basics about IGBT. Okay. Next is the structure of IGBT. So how we will be constructing this IGBT? Same. யார் கூட யார் mix பண்றோம்? MOSFET கூட I am going to mix the BJT. Okay. So for MOSFET, what type of substrate we have taken? We have taken
the aluminum.
no initially
Silicon.
what substrate? Substrate P type.
P type and N type.
That is the substrate. Okay. So we have taken P substrate. Okay. Later who will be here?
N type.
So next whom I am going to inject? N type. So the same here along with MOSFET whom I am going to compare? Include BJT also going to. So how means I am going to combine two N type. Okay. Since one is for MOSFET, other is for BJT. Okay. So all these are N type. Okay. Later that I am going to do compare, give one more layer that is of P type. Okay. Again one layer of N type. Okay. The P type substrate. Again another clear. Okay. So that is because we have studied MOSFET as a base. So in a P type substrate, N type to be doped, diffuse in it. So include BJT also I have to include. So BJT means there is also PNP transistor type semiconductor will be there. For BJT also PNP transistor will be there. Likewise for MOSFET also PNP semiconductor will be there. Either for we have to include these two, right? NPN in the form of NPN or in the form of PNP. Okay. So if you see that NPNP. Okay. Likewise here NPNP. This is the way to diffuse the MOSFET as well as the BJT to form the IGBT. Okay. So now here what is going to vary means this N will carry the Next, what we are going to do? We are going to diffuse for terminals, right?
Collector.
For terminals, here N here on diffusion, and later on here on diffusion, and later likewise here it is also going to be a diffusion. Upon that, who is this first? The diffusion yaar fill pannu? I am using MOSFET nu solta. I am using MOSFET as a base. For MOSFET, what is the name called? Metal oxide.
Metal oxide.
So who is that metal oxide?
Yes,
Si2. So P type substrate, I am going to diffuse N plus P, N minus. Later on, I am going to section for it terminals in the metal oxide. Okay. So the so-called terminals, what are called? Now. So one terminal is called as collector. Is there any difference? N plus N plus N plus N plus. Is there any difference? No. These two terminals are called as emitter. So we can join these two terminals and take it as emitter, collector, voltage source VCE. Okay, minus plus. So to whom we will be giving it to limit the current? Yeah, a resistor will be added to limit the current. Okay, later on. The next other terminal, what it is? Gate. So other terminal should not touch the emitter. It should go, but the one more voltage is given. To by whom we are going to control the IGBT? By using voltage, that is across the in their MOSFET it is VGS, means here it is going to be VG. Who is going to be there?
VGC.
Collector or VG emitter. Okay, so it should be connected to emitter. If you notice it, here I am not connecting, here it is connected. So what is this voltage called? Gate voltage, VG. We are connecting with emitter, you can name it as VGE. If in some textbook or in some reference book, if it is mentioned as VG, no problem. Okay. So now, here also whom I want to connect? Yeah, resistor for the current limiting purposes. Make it as R1 and this is R2. That is all about constructing the structure of IGBT. So, after constructing this, you want to know the working principle of it, right? So, initially, whenever there is a positive voltage which is being given to, it is what? Regulated power supply. Whom will be setting this voltage level? We. Okay. So, when doing as an experiment, we will be setting the voltage as, if it is positive means, here it is also the gate, by whom we are going to control it? The gate voltage. Okay. So, if this remains positive, initially there will not be any conduction. Once if the gate voltage is not changed, there won't be any conduction. There won't be any circulation of current, flow of current. Whenever I am increasing this VGS to a positive voltage level, whenever I am going to increase it, there will be, after increasing it, whom it is going to be? It is going to flow over the collector. So, this collector will inject the current. What it will do? It will inject the current. Okay. So, this collector terminal will inject the current. I am drawing it in dotted lines. Okay. Towards the drift region. We will be saying this is what? Drift region. Likewise, other side is also there, right? Emitter. From collector to emitter configuration. I told you two modes of configuration are there. Either in the collector emitter configuration or a emitter collector configuration. First we are holes. In p-type semiconductor, holes will be there, and in the n-type semiconductor, electrons will be there. So, how will we say that? Two currents are flowing there. Okay. So this current, you can say this as collector current. Whenever this current from this gate current flows through, it will give you the collector current, and the collector from the current from the P substrate, it is P-type. It is having the IH. It moves as the holes. Okay. Likewise, during the travel for the n-type region, it will move as the electrons. So the collector current is the sum of the hole current and the electron current. So whenever you are saying the I such as what? Hole current, that is flowing from the collector to the drift region, and this is the electron that is being flowing from the collector to the drift region. Okay, that is all about the working. Next is the VI characteristics of Igbt. So who is going to vary? Who is going to arise? Current? IC. With respect to who? Current? Sorry, voltage? Collector emitter, VCE. Who is going to control? Who is going to control this? Gate voltage. So with respect to gate voltage is connected to the terminal emitter. So with respect to VGE, initially due to some leakage current, there will be raising current. Initially due to some leakage, there will be some raising current. After that, what will happen? It will be in the, if we are setting VG as 1 volt. Okay. After reaching the threshold region, it will increase. Okay. Likewise, if I am increasing VGE 2 volt, it will increase. VGE as 3 volt, it will increase. VGE as 5 volt, it will increase. So we are going to control it using the gate voltage. So it is called as voltage control device. So VGE is here 2 volt, and here it will be a 3 volt and 5 volt. It goes on. Okay. So who is going to control? Gate voltage. Gate signal is going to control. By that, who is going to vary the voltage? DC collector emitter voltage with respect to the current. IC is going to arise. So initially I am saying this what? Initially due to the leakage current. In the operation itself I told you. In the gate terminal there will be some sufficient positive potential will be there. Okay. So this is said to be what means due to some leakage. Due to some leakage it will increases initially. After that it will the main voltage fix பண்றோமோ அதுல it will sustain. அதுக்கப்புறம் என்ன ஆகுதுன்னா it will reach out the threshold condition. இந்த device ஆல இவ்வளவு voltage rating தான் withstand பண்ண முடியும். Okay. So that is the threshold region. So in the threshold region this is said to be threshold. இந்த voltage ல கன்வெர்ட் கட்டாச்சுனா this is said to be threshold voltage. புரியுதா? This is threshold voltage. So in the threshold attain ஆகுது அப்படினு with respect to current பார்த்தா this is said to be threshold. இந்த axis ல இருக்கிற current. So this is threshold current. So the axis ல is voltage, it is said to be threshold. So beyond the threshold also the current will increase drastically. Okay. So அந்த மாதிரி sometimes peak ல போகும்போது அந்த device என்ன ஆகுது நமக்கு burst ஆகும். Okay. So this is the VA characteristics of the Igbt. So while we are seeing the switching characteristics with respect to time, how will be the voltage as well as the current. So we will be saying this as switching characteristics. Whenever what about the switches during on condition and off condition. Initially there will be some leakage. Okay va? அதுக்கப்புறம் என்ன பண்றேன்? voltage நான் increase பண்றேன். அப்ப என்ன ஆகும்? எனக்கு கொஞ்சம் increase ஆகும். Okay va? அதுக்கப்புறம் நான் என்ன பண்றேன்?
திரும்பி increase
மறுபடியும் voltage நான் increase fix பண்ணும்போது actually curve மாதிரி வரும். straight line மாதிரி வரும். Initially due to to some leakage, it will increases. If I increase the gate voltage, it will further increases. If I increase the gate voltage further, it will increases. So this is the IGBT's rating voltage setting. So anga adha extend pannu. After that, during turn off position, it will enna mari adu turn on acho the same way it is going to turn off. Okay, if you see this, it will be similar. Okay, so this current is due to leakage, and this is due to the sufficient positive potential at the gate terminal. Okay, and this is our VGE condition. Okay, so when it will increases with the, okay, first learn this, that is VGE. This period is said to be what? This period is said to be turn on condition. Okay, this is saturation region or sustainability region. After that, here it will become this. After this, this is turn off condition. This is the switching characteristics with respect to time for IGBT. So while drawing the VA characteristics, you will be first drawing curriculum here. So likewise switching characteristics curriculum. So that is all about IGBT. So one more characteristics we will be saying that transfer characteristics. Now suddenly the threshold voltage attained agade. So under what condition it is occurring? Initially
leakage.
the madri until side irukkumbodhu at some point it will increases. This is said to be threshold voltage. So in the voltage enna solrom appadina V eppo nadakudhu collector emitter ஒரு பாயிண்ட்ல என்னது threshold reach ஆகுது VGET. So VGET ல இருந்து தான் என்ன பண்ணுவோம் அப்படினா conduction start ஆகும். Okay, like this இந்த region இதுல இருந்து என்ன ஆகுது அப்படினா ரைஸ் ஆகுது இதுதானே. So that is எப்படி இருந்து இன்க்ரீஸ் ஆகுதோ likewise here is also increase. அதுக்கு மேல அந்த ரீஜனுக்கு மேல தான் என்ன ஆகும் conduction start ஆகும். Okay, so with respect to the current IC transfer characteristics, that is all about IGBT. So next we will be seeing about, now you know the operation for the 4 switching devices. Why? That we are going to apply it and connect it to its load. Okay, so we are going to see the, so initially I have told you that is for application from the unit itself what it is, control rectifier. Okay, so now we are going to study for halfway controlled rectifier, and here we are going to use the only the resistive load. Okay, that is we will be saying it as with or load. That is we are going to use only the resistive load. So you know the conception for halfway rectifier, that is our input side there will be our input source we will be giving to the transformer. Okay, so we will be having the primary and the secondary windings to across the transformer. Later we will be having the switch to control, that is for rectification conversion purpose. Okay, so what it is going to be here, we are using the SCR thyristor. Okay, so the next, which load we are using? I am going to give it for resistive load. So I am drawing resistance or resistive load of any resistive type. Okay, so now this is the terminal with the AC supply given to the transformer. Okay, and this is the thyristor, and the thyristor and here the voltage across the thyristor you will be seeing as in the graph. So we have to measure the voltage across the thyristor also. Okay, so how it will be working now? Whenever I am giving the AC supply, that will flow through the thyristor. Is the thyristor is when it will conduct during the forward bias the gate terminal, whom we will be giving? We will be giving the gate signal. We will be calling that as pulse, or you can say that as firing angle. That is firing angle of alpha. We can able to generate it from 0 degree to 2 pi or 0 to 2 pi. Okay. So whenever giving a AC voltage, what will happen? Towards anode to cathode. It will be in the forward conduction mode. The current will flow towards the resistive load. How this will vary based on by whom we are able to control it? We can able to control using the gate signal. So I am saying AC input voltage, right? So that is V in. What is the AC input voltage formula? V is equal to sinusoidal in nature, right? Voltage maximum into sin omega t. This angular frequency. AC voltage, which of course there will be frequency omega with respect to time. That is sinusoidal in nature. That is the voltage maximum into sin omega t. Clear up to this? The next step. Now, how the operation will be based on whenever giving a supply, AC supply towards from anode to cathode, the conduction of thyristor will be for a half-wave control rectifier. So this is sinusoidal nature. Since AC supply, how it will curve will be sinusoidal. Okay, so that will vary from everything will happen with respect to time. How the voltage? This I am drawing this for input voltage. So mark it as P suffix IN. Okay, so from 0 to pi over here, and over here the next cycle is pi to 2 pi. Okay, so initially draw the dotted line like this. It will be easier. Okay, so after drawing it, by whom we have to control it?
Voltage.
By to control the gate signal. Okay, so in gate signal whom I have to give?
Pulse.
Pulse. That is firing angle alpha. Okay. However, alpha will be with respect to time. Okay, so that is the angle we are going to decide. Okay, the firing angle can be decided as. Okay, the firing angle, take it as alpha. Initially now we don't know what is the value for alpha. So take it as this alpha. This is the firing angle alpha. And likewise for the, since it is half-wave rectifier, single mode of conduction will be there. Did you remember that half-wave rectifier function? Single mode, only the forward conduction mode. If one more the situation means we will be having the other mode of operation also, so it will become full wave control. Okay, so full wave rectifier, right? So this is half-wave rectifier only at the positive half cycle. Only the firing angle will be generated in the positive half cycle. So now given the firing angle, the next how the voltage will be. Okay, initially now margin. This is the firing angle which we have generated. Initially there will be 0 voltage. After giving the gate signal only, O2 is going to conduct, the thyristor is going to conduct. So then the voltage will fall. Okay, during negative half cycle there won't be any voltage. Till we are giving firing angle, there won't be any voltage. After reaching firing angle, again voltage is going to flow. Okay, this is the half-wave rectifier's voltage, output voltage with respect to time. The same thing will happen for the current also. Till this is for output current. Till the gate signal no current will be there. After the firing pulse there will be current, will flow like this. Till the next firing angle no current will flow. After the next firing angle the current will flow. Okay, so this is what the current waveform of the half-wave rectifier. Okay,
Yes.
clear? And how the voltage across the thyristor will be? The straight opposite to it, right? Current Let's write opposite. Here wherever the conduction, here there will be no conduction. Right? So you should go back. The same will continue again. Okay. This is the voltage across the thyristor. Okay. It is very rare to be asked. But you must know this output voltage and output current for the half-wave rectifier. This two is very important. Okay. How the output voltage and output current with the pulse they are generating for the input signal we are giving. Okay. Initially we have to say that the half-wave controlled rectifier's input AC supply is given via the transformer. Okay. So the AC supply will flow through the anode and there is a thyristor. So now listen, one thing also you have to remember. The transformer, after while we are giving it, we have to step down the voltage and give it. Okay. The voltage should not be above the forward and the reverse blocking voltage of the thyristor rating என்னவோ. Thyristor is a small electronic device, right? Small switching device. So it should not beyond that forward and the reverse blocking rating of the thyristor. The voltage which we are giving here from a transformer to the thyristor, it should not be above or it should not be greater than the thyristor's forward and the reverse blocking voltage rating. Okay, write it down. The thyristor, the input voltage should not be greater than the thyristor's forward and reverse blocking rating. Thyristor's forward and reverse blocking voltage rating. That is most important point. Okay. So after giving this initial voltage, the voltage which should not be greater than the thyristor's forward and the reverse voltage rating. Now the thyristor will conduct in the forward bias since anode is connected to the positive and its cathode. Of course, our next terminal is cathode. By whom we are controlling? We are controlling using the gate signal and we are seeing it for the resistive load. Okay. So based on this, we have to derive some formula that it is how will it be. That is, we are seeing it for output voltage, right?
Yes.
So what is the input voltage we are giving them? Input voltage is V suffix I, and since it is AC, the voltage is V max sin the sin. That is omega t with respect to omega is the angular frequency and time t is the time and V max is the maximum voltage which we are giving. Okay. So now listen for the output voltage or in half wave it is a rectifier circuit. Output voltage can be in nature of DC. Okay. So now for a complete cycle what it is? How the complete cycle positive negative complete cycle 0 to 2 pi. So it will be 1 by 2 pi. Okay. So the voltage VDC is equal to 1 by 2 pi of from initial during first half cycle. Where is from 0 to pi. Alpha where is from 0 to pi. During positive half cycle the voltage is V max sin omega t. Okay. From 0 to pi or the conduction is taking place from 0 to pi or alpha to pi. So we can't take that from 0 to pi because the conduction is starting from alpha to pi. So alpha to pi, the next, this is one form. Okay. The next addition to that, next half cycle is from pi to 2 pi. So the pi to 2 pi is there any voltage? So it will become 0. So I am doing integral of the range is from alpha to pi. Integral of, when you are putting it, you will be putting as integral of d omega t. Okay. So likewise 0 into d omega t. This is the full half cycle from 1 to 0 to 2 pi. Okay. And that is how. Now VDC is equal to, now the 1 by 2 pi let it be like this. Okay. Here is there any derivative integral reason is there? that. What about this? Upper limit minus
Lower limit.
lower limit. So while integrating sin omega t, we will be getting, we have to go to the 11th standard. Remember the formula. Sin omega t will become
1.
integral of sin omega t dt.
Cos minus cos omega.
Minus cos
omega
omega t. So it will become minus
cos omega t.
cos omega t. What will come in the place of omega t? The upper limit is,
Right.
so minus cos pi. Minus of,
Minus.
so this is minus cos
Minus
pi,
cos
right?
alpha.
Minus of, again it will become minus cos
alpha.
alpha. Okay, so the next 1 by 2 pi. So what is minus cos pi?
0.
Minus cos pi. Upper limit minus lower limit. So what about Vmax then? While we are doing it, so wait. So Vmax 1 by 2 pi into Vmax will be common outside. Okay, what is the upper limit first initially? Minus cos
Omega
omega t
pi alpha to
pi, likewise minus of minus cos omega t, the limit is here
alpha.
alpha. So you can replace omega t with pi over here, and here you can replace omega t with alpha over here. Am I right? So now, while integrating cos omega t, it will become minus cos omega t. Minus cos, upper limit is pi. It is upper limit minus lower limit. It is that minus. Okay. After that, while we are integrating sin omega t, it will become minus cos omega t. Minus cos, lower limit is alpha. Later,
Yes.
we can remind it as V max by 2 pi into, what is the value for it? Cos pi is minus 1. So minus cos pi is plus 1.
Plus 1.
Minus into minus will become here plus
Plus.
1 plus
As
cos alpha. So what is the VDC? It is V max by 2 pi into 1 plus cos alpha. Okay. So after that, if I substitute, if only, okay, the condition, if I generate the alpha is 0 degree means what it will be? Alpha is 0 means
0.
cos 0 is
0.
cos 0 1. Okay. So remember all these things. Okay. Cos 180 is minus 1. Cos 180, which means cos pi. Cos 180 is minus 1 means minus 1 of minus 1 will become plus 1. And here minus of minus will become plus cos alpha. And substituting alpha is 0 degree means it will become cos 0 degree is again. Remember this. Cos 0 degree is 1. So when we are substituting cos 0 as 1 means it will become VDC will become as V max by 2 pi into 2. I am cancelling it, it will become V max by pi. If I substitute alpha as 180 degree means it will become
minus 0.
so VDC will become
2 pi.
1 minus 1. So it will become
0.
0. Okay. So what is the maximum value of the voltage? V max by pi. What is the minimum value of voltage? It will be 0 based on the firing angle alpha. So if I push, which means I have placed the firing angle over near to 0. If I push it over here, till this voltage will be 0. If I push the firing angle over next time, so till that voltage will be 0. Firing angle there will be increase up to 180 degree, there will be voltage up to entire half circle, right? So that is the meaning of it. So now, if you know the VDC, what is the formula for IDC then? I equal to V by
V by
I am using resistive load only now. So I equal equal to
V
V by R. What is my V? VDC by R. So what is my VDC I have calculated?
V max by.
This is just condition, okay? When alpha is 0 degree, when alpha is 1 degree, after condition. But what is the formula? VDC is equal to V max by 2 pi. So then what is the formula for IDC then? V max by
2 pi.
2 pi into
1 plus
division who is here?
R divided
2 pi into R into 1 plus cos alpha. That is all about half-wave control rectifier with a resistive load. Initially, you have to say the transformer. From the transformer, you have to study AC voltage is given. The voltage rating should not be higher than the forward and the reverse blocking rating of the thyristor. So this is the rectifier circuit. So AC is going to be converting into DC. While conversion, how it is going to control? It is being controlled by the thyristor's third terminal, that is gate signal. So we are going to generate the firing angle. The firing angle is represented by the letter alpha. So the alpha we are going to generate from 0 degree to pi. Okay. So since it is half-wave rectifier, I have taken the input signal, that is a complete sinusoidal waveform. Half-wave rectifier will conduct only during the positive half cycle, since there is only one thyristor. Okay, only one forward conduction switch is there. Okay, and now what will happen during the forward bias condition? I have given some alpha firing angle. Wherever I am giving the alpha firing angle, at that point only the voltage is going to generate. Okay, the voltage is going to flow. Likewise, the current is also will be the same. In the half-wave control rectifier, the voltage and the current will be same, that is an in-phase condition. Okay, voltage எப்படி இருக்கோ அதே மாதிரி தான் current இருக்கு. அந்த condition என்னன்னு சொல்லுவோம்? In phase. இப்போ voltage வந்து 0 டிகிரில இருக்கு. current வந்து 30 டிகிரில தான் ஸ்டார்ட் ஆகுது அப்படினா நம்ம என்ன சொல்லுவோம்? out of phase of 30 டிகிரின்னு சொல்லணும். சரியா? சோ இங்க இந்த கேஸ் வரல, ஃபர்தரா வந்தது அப்படினா எப்படி சொல்லணும்? ரெண்டு டிஃபரன்ஸ் எவ்வளவு டிஃபரன்ஸ் ஆங்கிள் அதுல இருக்குதோ அது என்னன்னு சொல்றோம் அப்படினா out of phase 30 டிகிரி. out of phase 30 டிகிரி சொல்றோம். எவ்வளவு ஆங்கிள் ரெண்டுக்குள்ள டிஃபரன்ஸ் இருக்கோ அது out of phase னு சொல்லுவோம். Here voltage in angular converter the same way the current also. So we will be saying it is an in phase condition. Okay. So after drawing this graph, you will be deriving this derivation. This is a small derivation from the input voltage. V in is equal to V max sin omega t, and we have taken the omega z. We know that it is an angular frequency, and from that we know output voltage is, since it is the converted as DC. So output voltage we can say that as VDC. So VDC is equal to 1 by 2 pi integral of the lower limit what it is from the firing angle the conduction starts. So alpha to pi. There the voltage is controlled, right? So that is V max sin omega t. Another during the next half cycle there is no voltage. So from the pi to 2 pi, 0 d omega t. So applying the integral formula, applying the trigonometry values, we have obtained VDC as V max by 2 pi into 1 plus cos alpha. Okay. After that, we applied the condition. If alpha is 0 degree, what is the VDC? V max by pi. And if alpha is 180 degree, what is VDC? 0 volt. Okay. And the next, how the IDC will be? IDC equal to VDC by R. Okay. So in VDC formula, just we have to, in division we have to put a resistor. Since we know from Ohm's law, I equal to V by R. Okay. So if I need to control, find out the power means what we will be doing? P is equal to VDC into IDC. Power P equal to V into I only know. So power P equal to V into I. What is VDC here?
V max by
V max. So in IDC also there is a V max. We are going to multiply these two, right? So we can write it as V max square divided by 2 pi. 2 pi will become 4 pi square. Who is going to be the denominator? R. 1 plus cos alpha. 1 plus cos alpha will become
1 plus cos alpha d whole square.
1 plus cos alpha the whole square. That is the power delivered.